So today we're going to talk about graphs and models. In this section, we're going to cover increasing, decreasing, and piecewise functions and their applications. So if you want to pause this for a moment, go over the objectives. Let's move on. Increasing and decreasing and consistent functions. So whenever we have a function that rises left to right, so if I draw my graph out and it rises left to right, it can look, however, it rises left to right. We have an increasing function, which makes sense because we have negative infinity here, negative infinity here. So when we're rising up to some positive infinity, right? If it drops left to right, somewheres, then that's a decreasing function. But if I have a function that just makes a straight line, that's constant. Okay, because it's constant at some point. So this slide here, if you want to just take a minute to pause this, review it, this is just a good illustration and an explanation as to why this one's called an increasing function. So we have order pairs, right, of x comma y, but however, this case here, they said, well, let's let a go in the place of my independent variable x. And I know that if that's so, then my function is called f, and I'm still at that point, or plugging in that point for x, or looking for that point of x. We know that that gives me the y value. So f of a goes into the y value here. And then we have the b and then f of b. Okay, it says that if my a is less than b, so we got our a and b right here, the x values, implies that my function here of f of a is less than the function of f of b. We get an increasing function. However, if we look at this next illustration, it says that if my a here is still less than my b, so right here, still less than my b. However, the function of a is greater than the function of b, we're going to have a decreasing function. And then on this next slide, my mouse, there we go. We have a constant function. So it's telling me that whatever my value here on A and B, they're going to be equal. So my functions are going to be equal because they're going to happen at this one particular Y value point, right? It's going to be constant all the way across. It is a straight line. Relative maximum and relative minimum. So if you have a maximum, let me just show you a good illustration of it. But if you want to pause this, read it, that's the maximum. And then, okay, now pause this next part and read this. That's the minimum explanation. Let me just show you the most layman terms, the most easiest way to look at it. As if we're looking at mountains, right? The top of the mountain, that's its peak. That's the maximum point. So that's my relative maximum. The valleys, however, are going to be the low points. So we're going to call them our relative minimum. Okay. So let's do this first example. It says that we have two nurses that leave work and at the same time, right? And they make a right angle when they leave because they go different directions to go home. So a right angle tells me that I'm going to have a 90-degree angle in between them. And let's say this is the hospital. And it says Kara's speed, and she's traveled, let's see, 35 miles per hour. So we're going to assume that 1 hour has passed by the time she's got that because of the miles per hour. That is the statement here. And then it says that Mattis has driven 40 miles per hour. So what we're going to do now is we're going to find the distance, right? The distance between these two cars here. All right. Now, since we have a right triangle, we know that we can use the Pythagorean theorem to solve this. And so let's go ahead and acknowledge what each part is. So I know that D is going to be my distance, right? I know that T is going to be my time. In this case, it would have been X, right? But T is my time. All right. Now, saying that, I know that I have 35T plus my 40T. And I'm putting them in parentheses because the Pythagorean theorem says that I have A squared plus B squared is equal to C squared, where C is my hypotenuse, it's my longest side. So we're solving for our hypotenuse. So if we wanted to label this, we can call this C, right? And then we can call this one A and this one B. So now let's write it in that format. That means I got D of T. So my function's called D squared. I got my 35T squared plus my 40T squared. So now I got my model. So let's solve for this. So to solve for this, I need to go ahead and, well, there's more than one option to do here, but let's do this most easiest one right quick. If I was to do this, I need to undo, if I was to solve for the distance, I need to undo the square. And I know to undo the square, I would take the square root. If it was a cube, we'd take a cube root. But in this case here, it's a square. So that means I got to square both sides. You know, what you do to one side of the equal sign, we have to do to the other. However, we usually get a plus or minus because a square is a even root. So we'll get the plus or minus of this one side, but we're not going to talk about no negative distance because we're actually trying to solve the actual distance between them, right? So let's rewrite this. So now I got the square root of, and you could distribute this if you want to, 35 squared T squared plus 40 squared T squared. Now, we need to solve for these numbers, right? So if I solve for it, let's see, what do I get? 35 squared, which is the same as saying 35 times 35. I get, let me type it, write it in right quick. I get 125, or excuse me, 1,225 T squared plus 40 squared is 1,600 T squared. All right. Since the T's are alike, we can go ahead and add that 1,600 to the 1,225. And that gives me, let me scroll down just a little bit. That gives me the square root of 2825 T squared, right? So now let's take the square root of it. And I'm going to do approximately, okay? And remember, we got 2825 times that T squared. I can break it down like that if that helps you. It's up to you. So what I know now is 2,825 square rooted gives me a 5 square root of 113. And I'm going to bring that T out. I'm going to put it between the 5 and the root. You can put it behind the root. Just make sure it don't go in the root. Now, this would be exact, right? Now we need to get the approximation to the nearest hundreds. And so it's going to give me 53.15 T, right? So that this is all part A. I didn't get myself enough room, did I? All right. So since so what I can say, let me come right here. Distance is equal to 53.15. So T, since the time travel T must be non-negative, the domain is set at a non-negative real numbers. So I know that from 0 to infinity. So if I was to graph it, it would be 0 to infinity for the domain. That's part B. Okay. Okay, so this here is the solutions. If you want to pause it and read over it, here's the illustration, a good drawing here. And then here is the worked out part. So if you want to check it out, check it out. And let's pause there. So now let's do our next example. Our next example says, let's talk about a piecewise function. So piecewise functions are defined as using output for different parts of a domain. So we're going to use output formulas for different parts of a domain. And here is a good example. It says, say that we have f of x is equal to x plus 1, and it has this restriction where x is less than -2. Then we have f of x is equal to 5, where it has a restriction that it can equal -2, and it falls between -2 and 3, and it can equal 3 because look, it has the equal signs on the inequalities. And then it says f of x is equal to x squared, where x is greater than 3. So let's figure this out. If I just pick some values between all of this or around all of these, let's pick -5 for x, -3. This was f of 0. It kind of disappeared on us, didn't it? And then it came back. Let's pick f of 3, 4. So basically what I'm doing is I'm going to let x equal -5, -3, 0, 3, 4, and 10. So when I do that, I can solve for each one. So I can take this f of x equals x plus 1 and just plug in for x the -5, which gives me what? -4. If you want to make an XY table, oh, that would probably be great, and call one of them x plus 1, the next one equal to 5. That might be easier for you. But don't forget the restrictions on these, okay? So if I use -5, then I can use this formula here, right? When x is equal to -5, I can use it because x is less than -2 here, right? So if I use x is -3, well, that falls in here and here. So I got two options to choose from, right? If I use f of x is equal to 0, I can use this one here. Yep, and that's it. And when x equals 3, then I can use the x squared. So you got to look at the restrictions. Which one has a good x value? Which one actually stands true for it? This one would be for where x is equal to 4. Oh, I could also use this one here for x equals 3. Okay, so okay, so let's move on. So this is just letting you see the example. So what we're doing is we realize that we have the function happening, right? And they have the restrictions. So we got to pick values that's going to stand true for that restriction. So here we go. We have g of x is equal to 1/3 x plus 3. It says where x is less than 3. So I'm going to pick values where x is less than 3. It didn't say equal to 3, so I won't pick 3. If you notice right here, it has an open circle, and that's because it has no equal to sign here. So x equals 3 here, and then it says x equals negative, all numbers smaller than 3. So you know it's going to the left, but how? So you got to pick values all from here over, not 3, because it says it's not equal to. Plug in. So I was going to get that to erase. So by this point, we've already used the X and Y tables, plotting points, figuring out where it's at on the graph. So this is what we're doing. All right, so now when f of x is equal to the -x, and I'm make sure that that's not a typo on my paper. Yeah, it's just a typo. So I noticed that the restriction has an equal to sign on 3. So I'm going to put a dark circle right there. And it said x is greater than. So I know we're going off in this direction, but how? So let's pick points. You know, we're going to pick points 3 and over and plug it in for x. And then what does it yield? Then we can plot our graph. Okay. So this is the piecewise function. And what it's telling me is that I got this function and it's happening in different places and it has a different behavior. Okay. So take a moment to review this. If you have any questions, please reach out to me. Thank you.